Great. Well, hello everyone. I hope you can hear me okay. This is a new experience for all of us, including the fact that I'm quite pixelated for some reason. But welcome to the ISSST, or ICE, as you know, I like to call it, one of our first sessions here of the second day. So this is obviously a new experience for at least for me to be using Shindig, and it probably is for you as well. I've found that even just based on the training that I've done so far, it's pretty intuitive, which is great. One of the neat things that you can do is you can actually get into conversations with other people. You'll see if you kind of hover over someone that their name will show up and it will say, hey, you can start a chat with them. There's video chat. So, I encourage people, turn off your cameras. We specifically chose this platform because we wanted people to be interactive, and let's make that happen. So we have a great session here today, the first of 3 on large scale systems. The topic for today's presentations are going to be buildings and infrastructure, and also transportation and energy. We have one at 2 o'clock that's about circular economy, and 2 o'clock Eastern, I should say, is circular economy and life cycle assessment. And then one at 5:30 Eastern that's about buildings and infrastructure. Actually, I think, sorry, that one's on pavements. So anyways, lots to share here. A few housekeeping items. Please, we want this to be interactive. We've asked each of the speakers to present for 15 minutes, and I'll try and hold them to that. And then we'll do about 5 minutes for Q&A. Please go ahead and type questions into the chat. But we'll also have opportunities for you to ask them in person, which I think would be great. And the way that you do that in Shindig is you'll get promoted to the podium. So you can just raise your hand, and it would be great if you did that, just to help us have a little bit of a feel of what this is really like. So, okay, so I hope that our first speaker, Lixi, I think is here. Let me see if I can get confirmation of that, and we can promote her to the podium. Let's see. Ron, are you able to do that, or?
So I will be the first to present.
You're going to be first. Okay. So change of plans. That's good to hear. So
okay, I'm fine.
Okay, good. So what we have in the program, Yue is going to go first, and hers is listed as the second presentation. But Yue, I'd appreciate if you could go ahead and introduce yourself, and then you can also then share your screen.
Okay, I'm now sharing my screen.
Okay, let me see if it's.
Can you see my screen?
Okay. Yeah, we can see it. That's great.
Okay, good day, everyone. My name is Yue, and I'm the PhD student in Hong Kong University of Science and Technology. Today, I'm going to share one of my work, which we build the integrated agent-based and system dynamic models to simulate the market potential of decentralized water technologies and the impacts on water system. Actually, our research team mainly focus on the urban infrastructure modeling. And in this field, one of the major challenges is how to model the complex interdependence between urban infrastructure and the social economic environment. Actually, the complexity is driven by millions of decisions, such as the housing location, the community to work, places to shop, and your business locations. And this kind of decisions will drive the interactions and evolutions between infrastructure systems and the social economic environment. And this evolvement will again lead to the emergences of different properties such as land use, land cover changes, and the quality of life issues, as well as carbon footprint. By understanding the complexity, we wish to see more desirable amenities, such as the high tax revenues, and avoid the adverse consequences of improper city planning. And in this research, we focus on a specific research domain of urban water and sanitation services in the city of Boston, where the centralized systems actually dominate the water services for a long time. However, as centralized system approaches to its design lifetime, they are extremely vulnerable to the climate changes. And the decentralized technologies such as rainwater harvesting system, gray water recycling system are emerging as the strong potential alternatives to supplement the household daily water uses. Actually, this kind of decentralized technologies can reduce the water resource consumptions and reduce the dependence of aging centralized water infrastructures. It can also save a huge amount of money considering the system upgrades and extensions. But before the utility company can miss the investment and the government can better plan for the deployment of such systems, we need to first investigate the people's preferences. In other words, the market potential for such systems. So here in our research, we built up a bottom-up agent-based model to simulate the spatial adoption and diffusion pattern of decentralized technologies resulting from households' adoption choices. And you can see like in each round of the simulation, we will choose a certain number of households to formulate the samples, and we will calculate the agent's adoption utility based on their the agent's choice, the agent's preference, and the economic attractiveness and the involvement factors of the environmental benefits. Here the neighborhood choices, the influences here, and we will also calculate the household's decision based on like in other words, the household's choice decision will depend on the agent's decision with the most or the highest utility value. And for those households who didn't adopt any technology, they will return to the agent's pool, and they will still have the chance to join the next rounds of selection and simulation. In the agent-based model, we first created the synthetic households based on the personal and socio-economic characteristics of the household members. We also collected the property information such as the building height, building size, and the rooftop areas, and randomly allocate the household agents into the corresponding properties to finish or to complete the setup of the agents. And then we use the choice model to calculate the utility of each choice. And then we use the latent class, like the latent gold choice software to calibrate our choice model and calculate the conditional probability of class X here, of class X choosing option M. The software can generate the optimal number of classes and help us to better interpret our results. To validate our methodology, we predict the spatial distribution of early adoptions of decentralized technologies and compared our simulated results to the validated areas. Here you can see most predicted early adoptions fall into the validated areas in the north central downtown regions in the city of Boston, and some predictions may not be consistent due to the randomness of the synthetic household allocations. Besides the incompleteness of the observation data may also underestimate the area of early adoptions. While decentralized water technologies can help buildings save potable water resources, avoiding the unintended adverse consequences on the wholesale urban water system should be examined as well. So as the decentralized water supply decreases, because some portion of the water can be supplemented by the collected rainwater and gray water, we built the system dynamic model to simulate the dynamics in the reservoir water resource availabilities, hydropower generations, and the carbon emissions out of water supply and wastewater treatment. Here we also validated our results by comparing the simulated monthly reservoir elevations with the historical records in the reference year without any adoption of decentralized technologies. And based on both validation results, we can see our simulation results are basically in line with the reported data, and thus can prove the effectiveness of using our model to predict the spatial adoption and diffusion pattern of decentralized water technologies, as well as the impacts of the large-scale implementation of decentralized technology on the wholesale urban water system. Here we also visualize the spatial and the temporal adoption pattern of rainwater harvesting technology and greywater recycling systems, and we traced their diffusion trajectories. We can see the diffusion converges after 43 rounds of the simulation, and most single-family households prefer to install rainwater harvesting systems. The diffusion of the rainwater harvesting systems will start earlier from the north and central places and will spread later southwards to the southward communities, while the GWR, the greywater recycling systems, will diffuse from and mainly concentrated in the north central places and the southwest areas. By visualizing these trajectories, our results can be supportive to recognize the communities with high market potential, and such we can help the government to identify the high potential neighborhoods and accelerate the adoption of sustainable water technologies in a city. Our system dynamic results show that the Quabin Reservoir the Quabin Reservoir has more water during summer and autumn, as a huge amount of fresh water can be saved from landscape irrigation by using the rainwater or greywater instead. However, the hydropower generation decreases as less water will be transferred through the hydraulic turbines when potable water supply reduces. Reservoirs will discharge more water to downstream rivers to prevent their water levels from rising beyond the warning levels. Actually, it is for safety purposes, but it can also indicate a potential added hydropower potential. Overall, our system dynamic models suggest the significant trade-offs associated with the large-scale implementation of decentralized technologies, and also quantifying the trade-offs between the water saving and the hydropower energy reduction. And furthermore, we didn't find significant carbon reduction because of the high electricity consumption of greywater recycling systems. So in the future, we are going to explore the optimal deployment strategy for water decentralization to minimize the installation cost and energy used at the same time. By comparing the adoption pattern based on household choices to this optimal deployment solution, we wish to provide the insights to the city planners and the government for better designing and planning the innovation in a city. Okay, that's basically my research. So thank you for listening. If you have any question.
Great. Thanks very much, Yue. And apologies, you had to just look at me while Yue was presenting. I'm not sure. The person who was supposed to be helping us at the podium, I can't seem to find right now. So in any case, but I'm glad at least we got to see the slides, which is great. So any questions? As I said, there's all kinds of ways we can do this. We can, you can just type questions in the chat or raise your hand. We can promote you to the podium, which would be great. But like I said, just encourage folks to show your videos and ask some questions. So we'll see there's a join podium button up there.
Actually, I cannot see any one of you.
Okay, great. Well, hopefully you can see Matt, who's brave enough to step up to the podium. So thanks, Matt.
All right. Hi, Yue, and hi, everybody. I really enjoyed this. I'm a proud Boston resident and owner of some decentralized water infrastructure, some rain barrels, and I was very glad to see your emphasis on landscaping. I was wondering what other kinds of uses you imagined, or whether you had kind of envisioned a hybrid system. With landscaping, it's possible you have rain barrels and you don't need any pumps if you situate the barrels high enough so you can get enough pressure. But of course, that doesn't work for showers and toilets and so on. So in the systems that you looked at, did you have different types of adoption for different end uses of water?
Actually, here the decentralized technologies, they will provide water. The water will be only used for non-potable uses. For example, here is basically include the water for irrigation and the toilet flushings. And for gray water recycling system, there will be inflow, but the inflow only accounts the water from showers, sinks, and washings, about the laundries or doing washes, dishwashes like this.
Okay.
Yes.
Okay, thank you.
Thank you.
Great. Matt, are you? Oh, good. He could even step down from the podium. That's maybe what we have to figure out as well. Anyone else? Other questions or comments? Got it. Also, like Matt said, I'm also get my water from the Quabbin, so I am definitely very interested in this as well. What do you think are, you talked about this trade-off between greenhouse gas emissions and water, which is a tricky thing. Have you guys had any insights just to see are there other instances where people have had to play with some of those trade-offs and how they've supported it? Like, are there utility analyses, or how do you, like, even when you have this, Pareto frontier, it still means you have to have some type of a preference to actually make a decision. So have you seen much work in that space where people are looking at those trade-offs between water and greenhouse gas emissions?
Actually, here the trade-offs I found is basically the whole system trade-offs. Like when you implement some decentralized technologies, the water supply or the water withdrawal from the main centralized system will reduce. But for the reservoirs, because they will not allow the water level exceeding the warning levels, like for safety purposes, they will release the increased water, this water resources. But this kind of water actually can, because there will be the trade-offs when the water availability increases, but hydropower production reduces. However, this water cannot be used to generate more hydropower. So based on the current mechanism. So our team, the suggestion would be if we can modify the reservoir of this system mechanism, maybe this added water resources can be used to generate more hydropower. But this is basically the wholesale water system view from this perspective. We did not like investigate how each household, based on their preferences, can help to reduce this trade-off. Yes, maybe we will consider it in the future study. Yeah, thank you.
Okay. Great. Other last questions for Yue? Great. All right. Thank you very much. I think now we'll go back to our first presenter. I apologize. Is it Lixi or Lixi? Let's see. You have to. What you have to do is join the podium up there. That's great. Okay, great. Now we can see you. All right. And do you see the option to share your screen? Great. And what it appears is that, at least in this platform, if you're sharing your screen, we can't also see your video unless I'm told otherwise. That's at least the information I have. And because I'm on the podium as the moderator, you have to look at my video. So hopefully there's a way to kind of minimize it or to deal with that. But that's my understanding of how this works, why you're seeing my video while she'll be presenting. So, great.
Okay.
You had your presentation up there for a minute, and now it's not there anymore.
Okay, I was gonna ask if you could see that.
Not yet, no.
Okay,
Yep, now we can see it.
great.
All right, go right ahead. Thank you.
Thank you. Hi, everyone. Thank you for being here today for this talk. My name is Lixi Liu. I'm a researcher at the National Renewable Energy Lab. I'm here with my colleague and PI of this project, Janet. Janet will not be presenting today, but will be around to answer any questions that you may have at the end. The primary goal of this project is to identify deep energy retrofits capable of reducing average site energy use intensity by 50% in the Chicago housing stock. We partner with the local nonprofit Elevate to assess the impact of energy retrofits on energy, utility bill, and carbon emission savings at various granularities, including priority neighborhoods and building segments. Our research findings will support Elevate's next phase of the project, which is to perform a few validation of the proposed energy retrofits in selected Chicago homes. The building simulation for this project is done in an in-house analysis tool developed by NREL. RESTOC is a large-scale residential energy model for the contiguous US with 3 key features: a large representative housing characteristics database derived from numerous public and private data sources, physics-based modeling to provide realistic building simulations, and high-performance computing. We began by downscaling the model to the Chicago area. We calibrated the model then using energy use data for over 400,000 homes in Chicago. And with the help of Elevate, we refined housing characteristics by examining a variety of sources. Based on the census data today, Chicago contains over 500,000 residential buildings, or over 1.2 million by unit count. We modeled this as 22,000 individual units in RESTOC. About 40% of the homes are pre-1942, and another 40% are mid-century. Chicago homes are predominantly heated by natural gas with a saturation over 80%. These are the 5 priority housing segments that were identified by Elevate as showing the greatest potential for deep energy savings and for targeted outreach. They are single-family detached early and mid-century, as well as multifamily 2 to 4 flats. We began the analysis by exploring 61 individual upgrades for home improvement. We divided the upgrades into 3 general categories. Fuel agnostic thermal upgrades, which include air sealing, insulations, and facade upgrades. Multi-fuel equipment, which covered HVAC, water heating, dryers, and cooktops. And finally, easy upgrades, which include lighting and other appliances that can be swapped out without much labor. Here is the result for the first group, the fuel agnostic thermal upgrades. On the y-axis here, we have the individual upgrades, and on the x-axis, we have the metrics of interest. The upgrades are sorted by the first column, which is the average site energy savings from the highest to the lowest. The key takeaway here is that the air sealing and wall insulation are by far the best retrofits in terms of energy saved and by payback. Next, we have the result for the second upgrade group, multi-fuel equipment. The layout and the sorting is the same. We can see that the upgrades with the highest energy saved are overwhelmingly heat pumps for space conditioning. Most heat pumps could, on average, reduce site EUI by 20% or more. Mini split heat pumps in particular seem to take energy usage down even further by 40 to 50%. And because of this, heat pumps are a central component in our retrofit packages. And last, we have the easy upgrades result. These energy savings potential somewhat pale in comparison to the previous two groups. For example, a 50% reduction in plug loads could only really reduce site UI by 2%. Equipment and appliances in a house often interact and influence one another through different heat transfers. Some upgrades complement each other to provide synergistic benefits, while others do not. Here, we will look at how effective individual upgrades can become when they are combined to create retrofit packages. Based on our lessons learned in part 1, we examined 20 retrofit packages, 15 of which are shown here, and they're broken down into 3 groups. The first group we call utility incentive packages because they are designed to leverage existing incentives and rebates from ComEd and People's Gas in Illinois. These packages generally include envelope upgrades, appliance swaps, and some gas heating system upgrades. The second group of packages is based on the question of what additional upgrades can we add to the utility incentive packages to maximize energy saving potential. And for this, we added window upgrades, heat pump closed dryer, and HVAC heat pumps. The last group of the packages is intended to fully electrify the housing stock, with each package addressing a different segment of the housing stock. And these packages add just fuel switching for space heating, water heating, dryers, and cooktops. Here we have the package results broken out by the 5 priority segments. The y-axis here are some of our metrics of interest. By looking at the first row, which is the site UI savings, we see that the electrification packages and some of the comprehensive packages are consistently providing a site UI saving greater than 50%. In fact, if we look back at the previous slide, we can see that the 2 comprehensive packages, which are the 15 and 16s, are precisely those with the heat pumps. This result really highlights the value of heat pumps, specifically for space conditioning, in providing deep energy savings for residential homes in the Midwest and regions of similar climate. Now let's look at how the packages scale at the housing stock level and what they represent in terms of scenarios. From the packages in part 2, we created 4 scenarios. The first scenario, which is based on our simplest utility incentive package, represents a basic utility improvement scenario. The second scenario represents a more comprehensive utility improvement in that we are adding additional upgrades to further the energy saving. The third scenario is what we call deep energy efficiency with HVAC electrification. And the last scenario is full electrification, which we created by combining all of the electrification packages. Here we have the overnight total saving potential for the 4 scenarios. They're represented in the amount of savings possible if all upgrades were done overnight, as the savings are relative to today's market and environmental conditions. The savings are broken out by heating fuels, blue for electricity, and orange for natural gas. Keep in mind that the bars represent savings, and so positive means there's a saving, and negative means there's an addition to existing energy demand. And as we expect, the basic utility improvement scenario returns the least savings across the board, then followed by the comprehensive scenario. There are enormous savings from natural gas to be had when we electrify the housing stock. However, some of the loads that have been previously serviced by the natural gas are now translated directly as new load for the electric grid, which is why the blue bars for the 3rd and 4th scenarios are negative. So when we sum up the savings from each fuel type, we see high net energy savings for the electrification scenarios. The new additions in electric load from fuel switching is fairly minimal, thanks to the high efficiency electric equipment and appliances. However, due to today's rate differential between natural gas and electricity, these energy savings are translated into much smaller utility and CO2 emission savings. In fact, when we look at the CO2 emissions more closely, we see that the electrification scenarios did not do as well as the comprehensive utility scenario here. Because currently, on a per unit of energy basis, electricity in Chicago is 5 times more carbon intensive than natural gas. So in conclusion, deep energy retrofits are possible in Chicago. In particular, heat pumps play a key role in bringing the site EUI down to 50% or more. Not only do heat pumps provide good energy savings, they also have a reasonable median payback period of about 30 years or less. Secondly, air sealing and wall insulation provide cost-effective ways to save energy by reducing thermal losses. And given the Chicago grid today, which contains a high amount of coal on the margin, electrification may not provide as much CO2 reduction as non-electrification packages. However, electrification does not lock in gas equipment and appliances for another 30 years. And instead, it comes at the benefit of increasing return on investment as the grid decarbonizes over time. Finally, I want to caveat by saying that the actual savings and paybacks vary quite a bit by buildings, even though we did not really show the variability here in this presentation. And there are many interesting questions remain for further investigation in the near future, including in what situations or building segments will retrofit packages not lead to savings, and what are the thermal resilience and indoor air quality benefits of the retrofit packages. With that, I want to conclude and thank you all for paying attention and attending this talk. I hope you enjoy it. Jenna and I will take any questions you may have now.
Great. All right. Back on stage. We're figuring it out what to do, and fortunately, we figured out how to make it so that I'm not what you're seeing the whole time. So, as you can see, that the podium is now live, and so that's a great place to come up and ask your questions. You can also type them in the chat there. Raise your hand, and don't worry, Matt Eckelman. He set a high standard by joining us from a terrace in Barcelona or somewhere like that. You don't all have to be in a fancy place with nice weather and stuff like that when you join us. We have a great question. I don't know if can you see that, Lixi, or?
Yes.
Go ahead. Why don't you answer that? Did you see the question pop up?
I did. Is there a way to continue to see that?
That's what I wondered too. It went away quickly. Let's see. Okay, let's in the chat again. Let's see. Okay, go ahead.
So the main focus of the project has been on deep energy relationships, which is the DOE funded project that was started under the previous administration. The focus initially was on
Janet, unfortunately, I think we're having a little bit of trouble hearing you. I don't know if you can get closer to a mic or.
Is that better?
Oh, definitely. Yeah, that's much better.
All right. Yeah, I was using the wrong mic.
Okay, good. There you go.
So the main focus of the project is on energy savings. It's a DOE funded project, and they're really interested in the deep energy retrofits. City of Chicago is a partner on the project, as is ComEd, and the city in particular is very interested in carbon reductions. So what we presented here today is kind of a first pass on the CO2 reductions. We used 2019 e-grid marginal emission rates, so it's not a super comprehensive CO2 emissions analysis yet. I think some of our next steps are looking at the sensitivity of that. Particularly looking at future emission scenarios for the Chicago area and kind of understanding the sensitivity of that and the lifetime of some of the technologies we're recommending versus the rate at which the grid projected to decarbonize in the area. So I don't know if that exactly answered the full question. It disappeared pretty quickly.
That's great, Janet. Thank you. Other questions or okay, great. We got confirmation. It did answer the question, so that's good in the chat there. Thanks, Paul. Other folks want to step up to the podium. We've got 2 people who did it and survived, so we know it's safe. Yeah. Can you see the question down there in the chat, Lixi?
Sure.
Why don't you just read it aloud in case people can't see it exactly?
Sure. This
and
question
lastly,
is...
sorry, one other thing is we're kind of seeing now the Shindig platform. Why don't you stop sharing and then you can just be chatting with us. That's okay.
Okay. The question is from Aldrich.
Mm-hmm.
I hope I say your name right. Based on your conclusion, you had 3 suggestions. Which among those should policymakers, constructors, or designers prioritize in the short term to meet climate targets? Very good question.
Mm-hmm.
Let me go back to my conclusions.
So right now, like I said, we're seeing a screen that shows your Shindig platform, not your slides, if that helps.
Sure.
Okay, now we see the conclusion. Thanks. Go right ahead. Yeah.
I would say I think policymakers should try their best to prepare for the future as much as they can. I think the grid is poised to modernize and decarbonize with renewable energy and storage. And so I would say if they can invest in electrification packages, they should do so as much as possible to make way for the future, because you don't really want to lock yourself in for another 20 to 30 years of gas equipment. So that would be my recommendation.
You got to thank you there. So what do you think these places that are doing bans on natural gas in new construction? You think is that appropriate, at least in the Chicago area, based on this, or is the ban too stringent?
I would say in a place like Chicago, I would hesitate. As Lixi said, upwards of 80% of the homes are heated by natural gas, and electricity is much more expensive than natural gas. So you run into it's not just an environmental issue, but it becomes an equity issue really quickly. So I think we need not just overnight solutions like start banning natural gas, because you could inadvertently be creating this barrier to low-income households, especially. Just it's a cold climate, and access to heating is a necessity. But really, we need a combination of strategies that are targeting electrification long term. We'll come up with strategies for reducing the electric rate so that it is affordable for people.
Great. That's a really good point. It's not just about CO2.
Mm-hmm.
All right. Well, thanks very much. That gave us a lot of food for thought, a lot of good discussion. Thank you, Lixi. I also learned how I was definitely mispronouncing your name, either the ways that I thought it. So thanks for enlightening me for that as well. All right. Next, we're going to move on to the third presentation. Zhi Cao, or Sao, sorry, that I'm mispronouncing that as well. But Zhi, you're going to be brought up to the podium to do your presentation as well here, as long as you can be found. And great. All right, we can see you on the podium.
Okay, let me share my screen.
Okay. Something different now. We'll be talking about carbonation, cement-based materials.
Are you able to see my screen?
Yes, we can. We see the Shindig platform right now, and yep, now we see your slides. All right, take it away.
Okay, and thank you so much for having this opportunity to join the discussion from Belgium. My name is Zhi. I'm currently an assistant professor at the University of Antwerp, and the idea of this work was actually conceived during my stay at Northwestern through collaboration with Yue LI and Eric Massanet. And the main objective of this work is to develop a surrogate modeling framework to quantify CO2 uptake by cement-based materials. And this framework will ease the computational requirements for uncertainty quantification and sensitivity analysis. And more importantly, it will allow us to explore parameter space and conduct complex optimizations. So why cement-based materials carbonation matters? And cement-based materials carbonation is well known as a deterioration mechanism of cement-based materials. But its contribution as an anthropogenic CO2 sink is not equally recognized as compared to its contribution to CO2 emissions. And a few studies, and including our own study, have pointed out that a reabsorption of CO2 by cement-based materials is a significant CO2 sink, and offsetting around 20% of CO2 emissions arising from cement production, or 40% of processed CO2 emissions if we exclude fuels and electricity used by cement production. And future reabsorption of CO2 will become more significant, driven by growing population and mature needs. And to estimate the CO2 reabsorption by cement-based materials, we have to understand the mechanism of carbonation first. As we all know, the main ingredients of ordinary Portland cement include alite, Bilec, and calcium aluminiate, which have significant hydrolicity. And after mixing cement with water and aggregates, atmospheric CO2 dissolves in the pore water of concrete and forms carbonic acid. And the carbonate acid reacts with hydrated calcium silicates and calcium aluminiate. And this reaction leads to the formation of calcium carbonate, of which the process is called carbonation. And this process starts at the concrete surface, then slowly penetrates deeper over time. Although it requires a great length of time, cement-based materials carbonation will eventually soak up a substantial amount of CO2. While it could occur, in various life cycle stages of cement-based materials, the carbonation of cement-based materials is most complex in the in-use stage and in the end-of-life stage. At higher system level, the quantities of cement-based materials that stay in the in-use stage and in the end-of-life stage are determined by their service life, which can be characterized by a survival function and a density function. And to illustrate the mechanism, we regard the quantity of concrete consumed in the first year as time cohort 1, and the portion of time cohort the portion of time cohort 1 that stays in use, will diminish over time. And the portion of the time cohort 1 that enters into the end of life stage will climb up over time. And we use a carbonation function to describe the carbonation process in the in-use stage and in the end-of-life stage, except that the former is characterized as a slab, and the latter is characterized as a sphere. And the carbonation process is described as a function of the square root of time, and the coefficient K is subject to a wide range of parameters, including concrete additives, coating and cover, CO2 concentration, exposure conditions, calcium oxide content, shear of calcium oxide fully carbonated, particle size of end-of-life cement-based materials, recycling rate, etc. And initially, we used a physics-based model to parameterize these complex processes. And with this physics-based model, simulating cement-based materials carbonation is actually computationally expensive. And taking the United States cement and concrete cycle as an example, with a physics-based model, it takes 80 seconds to run a single simulation. If we were to run the simulations by 1,000 times, which is a reasonable but already small number, for uncertainty quantification, we would have to wait for almost 24 hours, which is essentially an entire day. We could, of course, disregard, the slowness and invest our computational budget directly to the simulations. However, this slowness is unlikely to be satisfying, for later optimizations when costs and emerging technologies that have impact on CO2 uptake are considered. You may want to start your simulations with different, starting points and different constraints. And also, when it comes to optimizations, even you have obtained satisfactory results, you may still want to further, investigate to see if a better trade-off can be struck between competing objectives. So the basic idea of surrogate modeling is to avoid investing your computational budget in answering the questions at hand. Instead, the surrogate model helps develop fast approximations to complex physics-based models. And having these approximations will allow us to implement fast uncertainty and sensitivity analysis, explore trade-offs in optimizations, and therefore gain more insights. While the basic idea of surrogate modeling sounds simple, the devil is in the details. The most urgent question for us now is what surrogate model is most suitable for approximating, the physics-based models. We started with Gaussian process, which is the most widely used surrogate model because of its interpretability. However, a Gaussian process model loses efficiency, when the number of features exceeds a few dozens. And using Gaussian process makes hyperparameter tooling super challenging, which is an essential step for training, the chosen surrogate model. So we turn to decision tree regression, which is more efficient and also intuitive for decision makers, compared to other regression models. We also employed gradient boosting to improve the predictive accuracy of our surrogate model. And the computational efficiency of gradient boosting decision tree regression also allows us to implement hyperparameter tooling more easily. And the traditional ways of performing hyperparameter tooling or hyperparameter optimization have been grid search or random search. And grid search is simply doing, an exhaustive search through a specific subset of the hyperparameter space. And random search replaces the exhaustive enumeration by selecting hyperparameters randomly. Here, instead of using these expensive hyperparameter tooling strategies, we employed a Bayesian, optimization strategy, which can iteratively evaluate a promising hyperparameter configuration based on the current model and update the model continuously. And this strategy could help us further expedite the training process. And as indicated in the graph here, our hyperparameter tooling starts with a few random searches and then concentrate on promising hyperparameter space in later searches. With this surrogate modeling framework, we are able to approximate our physics-based models and predict CO2 uptake by cement-based materials with satisfactory accuracy. And here we employed a five-fold cross-validation approach, which means the original sample is partitioned into 5 equally sized subsamples, and 4 subsamples are used for training, and the remaining one is used for validation. And apparently, the hyperparameter tuning has greatly improved the predictive accuracy of the chosen surrogate model, which is the decision tree regression model. And similar predictive performance is observed across output variables. While the predictive performance is satisfactory, our results also reveal that the predictions tend to be more concentrated around the medians. This is probably due to the initial sampling strategy, and in future research, we plan to improve the sampling strategy to cover broader parameter space. So to sum up, our first conclusion is carbonation of cement-based material is a complex physical-chemical process which requires consideration of multiple factors and expensive simulations. And our second conclusion is surrogate modeling could significantly expedite the simulations while satisfying accuracy requirements. And the next conclusion is trained surrogate models are potentially useful for uncertainty quantification and sensitivity analysis. And we also believe that our modeling framework will be useful for prospective modeling of emerging technologies that influence future CO2 uptake. And these emerging technologies include lower carbon chemistries, clinker reduction, CO2 curing, CO2 mineralization, linear construction, component reuse, waste stockpiling, and so on. And thank you for listening. And this is all for my today's presentation. And if you have any questions, feel free to ask. Thank you.
Great. Thanks, Zhi. I really appreciate that. Giving us a lot to think about. Let's see. It looks like we have a couple questions there. I don't know. Can you see them, Zhi, or do you want me to read them off?
It's in the chat. In the
Yep.
Let me see. Is there computational not?
Can you do parallel computation while you're running the simulations?
I believe you are referring to the decision tree regression model. Yes, indeed. The computation is parallelized. It's already parallelized. That's why the computation time is much quicker than the Gaussian process model.
Great.
Oh,
You see the next one down there too?
I didn't spot a quantification of performance of the surrogate. 24 hours becomes
like basically if it takes 22 hours to do the simulations without the surrogate, presumably is the surrogate instantaneous, or is it also require some calculation time?
So the first of all, the 22 hours. So it takes 22 hours to run the physics-based model, and for surrogate model, of course, it takes some time to train the model and to tune the model. But once you set up, the tuning framework and the training framework, it only takes like less than 1 minute.
Great. I think the less than 1 minute is where it's looking at. That the non-surrogate, I guess, is the simulations. Then down to that is less than 1 minute is great.
Okay. Thank you. Thank you for the question. Really good question.
Anyone else want to step up to the podium? We'd love to see some other people, new people. Great. While people are doing that, I was curious a little bit, your last slide there where you showed all the different ways in which this could be used. You had a whole, like maybe just give us, maybe as a prelude to what Dwarak's going to talk about, give us some examples of how it could be used in the CO2 mineralization space or CO2 curing. Like what are some ways in which the surrogate model might be used for that? Questions you might answer.
First of all, I have to start from the carbonation mechanism. So when you have so the potential of CO2 mineralization, and if you want to estimate the potential of CO2 mineralization, you need to understand how much of the concrete has been carbonated, and then you can estimate the carbonation potential for example, for end of life concrete or end of life cement based materials.
Mm-hmm.
And for CO2 curing, it's the same thing. So if you already implemented CO2 curing, then that means you have less, CO2 uptake potential, embedded in the end of life cement-based materials, and then with this understanding, you will be able to estimate, for example, how we can optimize the CO2 uptake. Should we implement more CO2 curing, at the construction stage, or should we, implement CO2 mineralization at the end of life stage? Because you want, I think next step is to find economic data, so you can estimate the cost for different technologies. And once you have the cost, and you will be able to evaluate the cost of implementing different CO2 utilization technologies, and then also you want to find out what is the optimum technology mix. So, and to find out this optimum mix, or the optimal mix of technologies, you will need some optimizations. And having this surrogate modeling framework will help you expedite the optimization process.
Great. All right, that's a great example. All right, there's another question that came into the chat from Aldrich. Great presentation. You've shown many design parameters in your methods, and I was wondering if you've determined which of those contribute largely to life cycle CO2 and its variability. So maybe just explain a little bit about the scope of what you're doing there, and how maybe if you're not able to answer this question specifically with this surrogate model, how you could help answer it.
So I think what you are first of all, thank you for asking the question. It's really relevant, and this is also one of the ideas we want to implement in the next stage. So I think you are referring to sensitivity analysis. This is exactly one of the benefits, of having a surrogate model. So you can easily conduct some sensitivity analysis based on the surrogate model, because you have inputs, and you have simulations, and then you can use different algorithms to test out how sensitive the results is to different to each parameter. But to be honest, I haven't done any sensitivity analysis yet, but that's already in the pipeline. Yeah.
Great. All right. Well, thanks very much, Zhi. Appreciate it. Great work. Congrats to you of moving all over the US and now going to Europe. So lots we expect from you over there in Belgium. So hopefully we can hear more next time as well.
Thank you. And really glad to reconnect with you. Yeah.
Great. All right. Last but not least, Dwarak, you've been fortunate that everyone before you did a great job on time. So now we have plenty of time for your presentation, and then also for some questions afterwards. So as we said, this was a good prelude to yours, because even though it's different life cycle stage, similar chemical mechanisms going on with your talk about mineralization. So
yeah.
Go right ahead and share.
So thank you, Jeremy, for that introduction. So yes, I'm going to talk about carbon capture and utilization pathways to generate the highest climate benefit, not just restricting myself to concrete, but also expanding the scope of the research, chemicals and minerals along with concrete. So the question is simple. If you had 1 kg of CO2 from an environmental perspective, would you utilize to produce concrete, chemicals, or minerals? So that's the topic of today's talk. Just a short introduction. I'm Dwarak, and I'm currently a scientist at NRED. Before I like to start, I'd like to acknowledge the following organizations that have been instrumental in funding and supporting this research: NREL, the Global CO2 Initiative at the University of Michigan and the Center for Sustainable Systems at the University of Michigan. A call out to my collaborators, Gregory and Shelley Miller Fulker-Sick from UMich, and Joshua Shadley at NREL. So with that, a brief agenda introduction. What exactly is carbon capture and utilization? How can we apply this method of LCA called anticipatory LCA to quantify the relative climate benefits of CCU pathways, methods of analysis, and which CCU product generates the greatest climate benefit? By CCU, I mean carbon capture and utilization. So a brief introduction to carbon capture and utilization. So what exactly is carbon capture and utilization? In its simplest form, it can be referred to as a specific circular economy strategy for CO2 waste emissions. So what exactly happens in CCU is that we have emissions from multiple industrial processes occurring globally. So you capture the CO2 and you make use of the CO2 as a feedstock to produce valuable products, concrete, chemicals, aggregates. So basically you're closing the loop, you're preventing atmospheric CO2 emissions, and also you have an economic incentive because these products that you're generating are commercially valuable. So it's not just an environmental benefit, but also an economic benefit. And as a result, there's been a lot of funding and support and scientific interest in this area of carbon capture and utilization. The 45Q policy initiative in California state and across the country in the US is a great example of that. So in fact, if you look at it, a recent study showed that if you look at the left half of this slide, there's a lot of potential to utilize CO2 in gigawatts at the scale of gigatons rather for CO2 utilization potential in the future. You can see the big blue bubbles over here. If you look at the right side of the screen, you have a significant economic potential to scale up technologies. A lot of these technologies, in fact, most of them are in the emerging stages. So this is a report on the potential rather not on the current state. So there is a significant amount of revenue to be gained and climate benefits to be gained from expanding CCU operations globally. So I'm going to talk about anticipatory LCA and how to quantify the relative benefits. So this is the typical system of looking at the CCU space. How do you apply LCA? So basically what's happening here is you capture CO2 and you use renewable electricity because a lot of these chemicals that are produced to CCU require hydrogen, and the best way to generate hydrogen from an environmental perspective is through using water electrolysis supported by renewable electricity. And because of the technology development, you can make use of CO2 to produce concrete, chemicals, or minerals. However, there are some key limitations in the existing LCAs of CCU technologies. Beyond quantifying the climate benefit based on CO2 utilization, there is a lack of a robust method to compare the different pathways. So where exactly can we use CO2 to produce maximum benefits? Is it concrete, chemicals, or minerals? Obviously, we have the issue of data uncertainty because a lot of these technologies are in the early stages of R&D. So we know that there's going to be an issue with data uncertainty. How do we guide technology developers in identifying promising research and development strategies to maximize the climate benefits from CCU technologies? How do we account for system aspects? Because we're going to use renewable electricity, is there a better way of utilizing the renewable electricity? Can we supply the renewable electricity directly to the grid to offset CO2 emissions on the grid, especially when the grid is dirty, instead of making use of renewable electricity in CCU applications? So that's another system aspect that needs to be rigorously and robustly evaluated. Also, there's another challenge from a purely life cycle perspective. When we make use of carbon dioxide to produce products, sometimes the material properties of products changes. For example, when you make use of CO2 to cure concrete, while the mass of concrete is identical, the compressive strength, the durability of concrete can change. So from a functional unit point of view in an LCA, that introduces challenges. So in order to address these challenges, I've applied this anticipatory LCA method of evaluating CCU technologies. So I'm going to start from the left. I'm going to account for the potential better uses of renewable electricity. For example, supplying into the grid. I call this the environmental opportunity cost. I'm going to evaluate emerging technologies and incorporate uncertainty assessment. At the same time, also identify ways in which we can guide technology developers in the early stages of technology development. The entire analysis is going to be done on a comparative basis, not an absolute basis. So I'm going to evaluate the climate benefits from utilizing 1 kg of CO2 across different pathways. And I'm going to account for other aspects like what I just mentioned. I'm going to account for properties, changes in material properties because of CO2 utilization when comparing the different technologies to utilize CO2. So this is my approach at a high level. So I'm going to get down into the details a little bit, but just a little bit. So I'm going to compare CCU pathways. So the basic assumption here is that when I'm going to produce a CCU product, for example, CCU methanol, I'm going to offset the conventional pathway of producing methanol. So that's the basic underlying assumption. So this is the system boundary for the CCU technology. I'm going to capture CCU from carbon dioxide from a natural gas power plant, and I'm going to utilize it across producing concrete, chemicals, and minerals. For certain chemicals, we need wind electricity to electrolyze water to produce hydrogen. For example, in certain CCU chemicals like methanol, we need hydrogen feedstock too, especially if you're going to produce it from CO2. And the basis on which I'm going to decide which pathway is the best from a climate perspective, I'm going to use this metric, a novel metric called the climate return on investment metric, to decide where exactly do we invest that CO2 to maximize climate benefit. So these are the broader system aspects from a CCU pathway. So I'm going to compare this with the conventional pathway, because if you're going to produce a product through a commercial product and through the CCU pathway, we're going to offset a conventional production. So in the conventional production, because there's no carbon capture, the emissions from the power plant is going to occur directly into the atmosphere. The wind electricity is going to be supplied to the grid instead of being used in CCU. So that's the opportunity cost. And we have the conventional way of producing the material or the chemical or the product. So that's what is going to be offset if you're going to use the CCU pathway. The conventional pathway is going to be offset. So in terms of the details, I've collected data from the inventory data from 99 data sets through an exhaustive literature review, 69 data sets for chemicals and 26 data sets for minerals. And I've used CIMAPRO and EcoInvent to determine the life cycle CO2 impacts, both in the CCU pathway and in the conventional pathway. So in terms of the products or the pathways, I'm going to evaluate 20 different products, 4 concrete, 13 chemicals, and 3 mineral pathways. So I'm going to evaluate the relative climate benefit across these 20 products. So I was referring to the climate ROI metric. So what exactly is the climate ROI metric? The climate ROI metric, without getting into the details too much, it's a simple unitless metric. It's a ratio. So the numerator of the ratio determines the amount of CO2 that's avoided per functional unit of the product. The functional unit can be mass, it can be compressive strength for concrete, the mass for chemicals, or the mass for minerals. So I'm looking at different functional units. So this is one key advantage. It helps harmonize across different functional units when I'm comparing the 20 CCU pathways. And in the denominator, I'm going to look at the CO2 utilized per functional unit of the CCU product. So basically, this gives me the amount of CO2 that is avoided from a broad life cycle perspective per unit kg of CO2 that is utilized in producing a specific product. So the implication of this is that the greater the value of climate ROI, the greater is the climate benefit that is generated, especially if it's greater than 0. If the climate ROI is less than 0, that means despite utilizing CO2 from a life cycle perspective, you're increasing climate burdens. So this is the key aspect that you need to consider. If it's greater than 0, it's good for the climate. If the climate ROI is less than 0, it is bad for the climate. So this is what I'm going to refer to in the future slides. So I'll not get into the details. So how do we interpret the results? So first I'm going to start off with an absolute assessment. So I'm plotting the climate ROI, and because I'm accounting for uncertainty in data, it's going to be a distribution. So I'm over here for an illustration, I'm comparing 2 pathways, concrete and formic acid. concrete, the functional unit is megapascals of compressive strength, and formic acid, it is 1 kg of the chemical that's produced through carbon capture and utilization. So this percentage value over here gives you the likelihood of the climate ROI being greater than 0. That is the likelihood of a climate benefit being produced by concrete, CCU concrete being produced. So similarly, the likelihood for formic acid is 96%. So what happens is that here we see that concrete has got a likelihood of producing a climate benefit by 70%, and the same value for formic acid is 96%. So that's what these numbers in the brackets mean. So this is just the 2 pathways. So I'm going to expand it to the 20 pathways. I know this graph is a little crowded, so I'm going to just focus on the key findings. The first part is, as you can see here, there's significant data uncertainty when we try harmonizing across the different data sets. So that is typical of emerging technologies. You can see here that the climate ROI varies between -15 and 15. In fact, there's a much significant variance. That's the reason I've isolated some of the other pathways in this inset graph. So some of these pathways are really bad for the environment, at least based on the current state of the art. The climate ROI is really negative, which means that from a life cycle perspective, we are increasing climate burdens. But in terms of the winners, so in terms of the absolute assessment, these 4 pathways, the production of carbon monoxide, the production of formic acid, and 2 pathways to produce concrete, from a life cycle perspective, they have a very high tendency, as you can see, from 70% to 100% in terms of generating a climate benefit. So these 4 pathways are very promising. The second key finding is that the use of renewable electricity, it's better off to supply renewable electricity to the grid, especially when the grid is dirty. It's very carbon intensive, rather than use it for production of hydrogen in order to produce CCU chemicals. So you rather use that wind electricity directly on the grid rather than using it to produce CCU chemicals. As you can see here, the percentage value of climate benefits for a chemical like methanol, it drops from 42% when we consider the environmental opportunity cost, it drops to 0. So you rather use renewable electricity on the grid when you account for alternate applications of renewable electricity. So this was the first key finding from an absolute assessment perspective. So the next part is I'm switching the analysis to a relative mode of analysis. So in the relative assessment, so we have this entire set of values, simulated, calculated, estimated values of climate ROI based on the Monte Carlo assessment. So what I'm going to do is I'm going to conduct a pairwise comparison. So here I'm comparing P2 with P11. So this value over here in this heat map, the heat map gives you the results. There's a 70% likelihood of P2 concrete having a better climate benefit than formic acid. So P2 is preferable to formic acid in terms of CO2 utilization based on the climate benefits that are generated in 70% of the total Monte Carlo runs. So that is the way I've designed this heat map table over here. As we go down the table, you have the climate benefits are reducing. So basically, the pathways on the top tend to produce a greater climate benefits as indicated by this heat map over here. Also identified the hotspots. What is it that's contributing to the climate burdens in the pathway? So in this pathway, the use of OPC, that's ordinary Portland cement, that tends to be the hotspot for the production of CCU concrete through CO2 mixing. So basically, you have to understand that the pathways that occur in the top rows, they tend to produce a greater benefit, climate benefit than the pathways that occur lower in the table. So I'm going to extend this analysis to all the 20 pathways that I've evaluated this heat map analysis based on a pairwise comparison. So as you can see here, the top rows, as I mentioned, tend to produce the greatest climate benefit. So what's happened in this relative assessment is that the findings still hold. The 4 pathways which produce the greatest climate benefit per kg of CO2 utilized are the 2 mixing pathways for concrete and carbon monoxide production and formic acid production. You ideally want to avoid these pathways which are at the bottom of the table based on the current state of the art in the early stages of technology development. And in terms of the hotspots, for the chemical pathways, energy use in the form of electricity and steam are the key contributors to the climate ROI metric. So if you can reduce energy consumption when producing chemicals. It'll increase the climate ROI and the climate benefits. And for concrete, what you want to do is you want to make sure that your compressive strength doesn't decrease when you utilize CO2. And that way we can reduce cement consumption on a per megapascal basis of compressive strength. So you want to make sure that your compressive strength doesn't reduce when you utilize CO2 to produce concrete. So these were some of the key findings from the relative assessment. The 4 pathways produce the greatest climate benefit. So with that, I'd like to close. In summary, I've identified 4 pathways which produce the greatest climate benefit per kg of CO2 utilized. Based on the current state of the art of CCU products, the technology used to produce them, and the state of the grid, it's better off to produce renewable electricity, supply renewable electricity to the grid. And as I've shown you, the application of anticipatory LCA helps address issues of data uncertainty in the early stages of technology development, compare the different CCU products for climate benefits, and also help guide technology development. With that, I'd like to close the presentation. Thank you so much for your time, and I'm open to questions now.
Great. Thanks very much, Dwarak. You gave us a lot to think about there. Any questions from folks? Please step up to the podium, put it in the chat, whatever you prefer. Great. Another MIT person. Good to see you. Right.
Yes, hi, nice to see you too.
Go ahead.
Great presentation. I had a question. I noticed that you had 2 different ways of making formic acid, at least 2. One was via hydrogen and the other was via direct reduction, I believe.
Yep.
And so it kind of seems like a cool case study, right? Because you're making the same product, and I think you said everything's coming from wind, right? So you've got the same energy source, you've got the same product, but you had very different environmental impacts estimated from them. If I remember, it's like slide 17, or I'm sure it also showed up here. So it seems to really be focused on like the actual production method, be it. Could you kind of describe why you found a huge difference there?
I think in one of the pathways, you are electrolytically reducing CO2 first instead of hydrogenating CO2 directly. I think that's the reason. Because the electricity consumption to reduce CO2, it's much higher using electricity than hydrogen. Instead of a catalytic pathway, you're using electricity to directly reduce CO2 in something like a solid oxide fuel cell. I think, again, I need to go back and see what exactly is happening in each pathway, but I think that's the reason my initial assessment is that. I can get back to you after going through the paper in detail, because each of these pathways, I don't know what exactly is happening. I mean, I can't, it's not at the tip of my fingers now. But I think the production pathway matters. And one of the pathways you are using electricity to reduce CO2, and the other pathway you're using hydrogenation of CO2 using catalysis.
Great. Thank you very much. I appreciate that.
Great. Thanks, Micah. There's a question from Zhi that's in the chat. I can read it for you, but he says, great presentation. Could you comment on why CCU technologies are not taken up by industry? What are key barriers in addition to costs, which is obviously a big one, but clearly not the only one. So maybe, what are some of the other barriers there?
That's a great question. There are multiple reasons. One is in terms of policy clarity. It's still, even policy is in the emerging stages. For example, 45Q is a great example, and there's been some thrust of late to actually help boost CO2 utilization rather than just CO2 sequestration. So unless you get the value for CO2 utilized in terms of an economic value, the incentive is there to utilize CO2 rather than just capture and sequester. That's one key aspect. You need the policy clarity. The second one is there's a lot of other infrastructural developments that need to happen. For example, okay, you have this process to produce a chemical through CO2, but you need pipelines to supply the CO2 if you want to scale it up. So that's another key constraint. Unless you have infrastructure support to transport CO2, to capture CO2 at a large scale, which is already existing, you won't have players manufacturing chemicals or concrete. So that's another constraint. The third aspect I would say is that how do we collaborate findings? How do we help communicate findings, especially for a lot of these technologies are in the early stages of technology development. So how do we help inform policy decisions from a science perspective that needs to happen? So these are some of the reasons that I could think of. Policy infrastructure and R&D support needs to expand.
Yeah.
To summarize it.
Yeah. I wonder if it's also, like you said, just that even though maybe at a chemical standpoint, you're producing a lot of the same stuff, there's still maybe mistrust as to whether or not the performance will be the same, or certainly in the concrete and aggregate side, there's some concern. I don't know about the chemicals as well, but.
And also, the other thing I forgot to mention, a lot of these chemicals are cheaper to produce from the conventional pathway rather than the CCU pathway. So there's that cost challenge too.
Yeah.
Currently.
Yeah. And that was one that, Zhi clearly mentioned. We know that's going to be one, but if we have to deal with cost and other issues as well, that just adds to it even more, right? So, other questions, or like I said, step up to the podium or put them in the chat there. Great. There's one that oh, go ahead, Yuan. Yeah.
Hey, hello. Thank you for the presentation. I really like it. I guess I have two questions. The first question is, your ROI really depends on what avoid product you chose. And both carbon monoxide, formic acid, they can be produced from both fossil fuels and also biomass-based pathways, which usually have much lower carbon footprint. So I'm wondering, like, which pathway you chose. This is my first question. My second question is, how do you deal with the end of life of those products? I mean, if they are used in some product or they are used in fuels, finding the carbon still be released to the fuel, related to the atmosphere. And I remember in your presentation, your CO2 sources are CO2 coming from the industry, right?
So the power plant.
Yeah, so I'm wondering, like, whether this will be the better pathways, or those CO2 coming from the industry will better to send them to some places for permanent storage while using biomass to sequester the carbon and produce all these chemicals we can do.
So I'd like to answer the second part first. In terms of the CO2 being re-released at end of life. So the assumption here is that that's anyway going to happen. So whether I'm going to produce for example, methanol through the conventional pathway or methanol through the CCU pathway, that methanol is going to be used and it's going to be released. The CO2 is going to be released back into the atmosphere. So that can be compared on an equal basis. So I've not considered that as part of the modeling. We have stated that clearly. The re-release of CO2 back into the atmosphere is going to happen any which way. So that can be removed from the analysis. With respect to the first question, which pathway of conventional material is being offset? We have used the one that's there in EcoInvent because so that tends to be the conventional fossil pathway of producing the chemicals. For example, if methanol is going to be produced of formic acid, we have considered the traditional pathway of producing methanol from fossil fuels or formic acid from fossil fuels. So that is a limitation of the analysis, but the analysis can be expanded to include multiple pathways of producing the chemical through the conventional means, either let it be from biomass or from fossil fuels.
Thank you.
So a key reason for that is we needed to find out what is the most widely used conventional pathway of producing a chemical or concrete. So that's the baseline that we have used.
Great. Yeah, that really depends on the country. In the US, Mexico, they're very different if you choose to another country. I guess my second question is actually, your CO2 sources are actually fossil carbon, right? Yeah. And then you capture those fossil carbon, you turn them into some chemicals or concrete. After those products reach their end of life, those fossil fuel carbon come back to atmosphere again. So that's why I'm asking why those pathways would it be better or more favored than just using biomass to produce all those chemicals, because they are part of a biological carbon cycle.
Yes, so that is something that we can do in the future. So for now, we have not incorporated CO2 capture from the combustion of biosources rather than fossil sources. So our basic assumption is that we'll use the power sector as a good indicator of supply of CO2. We didn't expand it to different sources of CO2. That's something that we can definitely do in the future. So we started off with the power plant scenario, the fossil power plant.
Great.
Thank
All right.
you.
Yuan, for the question, and thanks to Dwarak for the great presentation. There's another question that's down in the chat a little bit about the ROI. We're at time, so I'll just do a few quick announcements, and if you want, while you stop sharing your screen, you can see if you can respond to it. But thanks, first of all the presenters. As I said, they did a great job being on time. The other thing that I like about this session is it really framed the broad differences that we've had in large-scale systems for buildings and infrastructure, and that really helps us set the tone for the next two sessions that I hope you'll join us at. One is coming up at 2 p.m. Eastern here, and then the other is at 5:30 Eastern. I also wanted to put in a pitch for, there's a poster session that I saw Derek on here. He's worked hard to help organize it. That poster session is at, at 4 p.m. Eastern. One of the neat things about it, it'll be a great way to try and, use this platform a bit more. You can, it's easy to get into small group discussions with people and to hang out with them. So that's a great way to do it. And then the other pitch that I wanted to give is that tomorrow at 2 p.m. Eastern, one of the plenary sessions is a discussion about a movie called Picture a Scientist that focus a lot on what it's like for women to work in the fields of science and engineering and things like that. And you should have gotten a link to be able to watch the movie in advance. We have a great panel discussion. And so that's tomorrow at 2 p.m. Eastern, if you could join that. So hopefully I'll see everyone throughout the conference, and also back for this particular session at 2 p.m. Eastern. So thanks very much, everyone. All right.